Hello everyone. In this talk I will present the main results of our long-term empirical evaluation of the presence, composition and lifetime of technical debt in open source software. I will start with a brief introduction of technical debt, some of the widely available tools used in both research and practice, as well as their strengths and weaknesses as identified in recent research. I will then walk you through our case study, after which I will present our most important conclusions. Let us start. We find technical debt first mentioned by Ward Cunningham in 1992, who opined that taking it on can speed up development and was not actually a problem, as long as it was resolved soon after introduction. Later, Fowler provided a more complete characterization by describing technical debt as a software quality deficiency that made development and maintenance more difficult. Like the financial counterpart that inspired its name, technical debt comprises a principal and an interest. Existing research identified that over the long term, the interest tends to compound and overwhelm the development team, who in many cases were forced to stop development and switch to refactoring. While already hinted at by Cunningham, timely refactoring is in many cases sufficient for handling technical debt. In practice, this is in many instances neglected due to time and budget constraints, which allows the interest to compound as one suboptimal decision leads to the next one. Continued interest from both researchers and practitioners in technical debt has led to the development of many tools that aim to measure and characterize it. Most of them are built on top of a software quality model and use static analysis and software metrics to provide a quantitative evaluation. In our research, we employ the SonarQube platform, which is based on the scale model, one of the most widely used quality management platforms. Recent empirical research has examined widely used tooling, with both strengths and weaknesses being reported. Most important strengths, and the reason we based our case study on SonarQube, is that tools provide a measurable evaluation that allows directly comparing results across versions and also across applications. On the other hand, main reported weaknesses include inconsistencies between quality models, as well as reported results, translating rather poorly to documented software defects. These must all be included in the context of our present and future efforts. Our main objective was to investigate the presence, the characteristics, and the long-term evolution of source code technical debt in the context of open source software. We operationalized the main objective into 3 research questions, and we carried out our case study according to the best practices that were outlined by Runeson and Host. The first step regarded selecting target applications. We narrowed the search to cover a common type of applications, from which we selected 3 popular open source apps. Altogether, we selected 110 versions that were released by the developers in our case study. In the cases where several releases happened in the span of a few days, we only considered the last one, as most likely this was the result of last-minute bug fixes. The table illustrated the earliest and the latest release for each application, together with some key technical debt information. Notice that our study covers over 10 years of development history for each application, and that a significant increase in both application size as well as reported issue counts. SonarQube reports technical debt in terms of the time that is required to fix it, which is illustrated on the rightmost column. Here too, increased application size contributes to more effort that is required to fix the identified issues. After selecting the versions to be included in our study, we thoroughly examined the source code of each version in order to ensure that library and application code were not bundled together. We started each version and made sure all functionalities were working as expected. Each version's source code was imported to a Sonar server that we configured to recognize consecutive versions of the same application. This allowed Sonar to close more than 37,000 issues that were no longer detected in newer versions. We made available the entire collected and processed dataset in the form of a replication package in order to facilitate replicating or extending our study. We now proceed to answer the 3 proposed research questions. First, we examined the technical debt that was identified in each application version. The dotted line represents application size, while the hashed areas show the ratio of technical debt. The debt ratio here represents the percentage of total development time that is required to fix all identified issues. In the case of FreeMind, we notice a large spike at version 0.8.0, where the debt ratio exceeds 9%. This means that 9% of the total estimated time spent on developing the application is now required in order to fix all detected issues. The darker hashed area shows that most of this depth was new to version 0.8.0 and was subsequently eliminated in version 0.90 beta 17, after which the application remains stable. Now, in the case of JEdit and TuckGuitar, we do not observe such sudden increases in technical depth. Both applications increase in size over their development time frame, and the ratio of depth seems to have a slow but steady decrease in both. Spikes, such as observed in JEdit 4.0 or TuckGuitar 1.0 release candidate 1, accompany the inclusion of many new functionalities, as also evidenced by the version number changes. Especially in the case of TuckGuitar, we noted a very good technical depth ratio that was less than 3% over its entire development history. Now, in order to answer research question 2, we looked at the composition of technical depth as identified by SonarQube's type and severity issue tags. We note that issues labeled as code smells would require most of the fixing time. Of course, this might be misleading, as in many cases, issues that were labeled as bugs or as vulnerabilities might better translate to actual defects in software. As such, we also examined the effort distribution according to issue severity. And we discovered that critical and major issues made up most of the effort in the case of all three applications. In all cases, we recorded low values for the standard deviation, which shows that our results are consistent both longitudinally, which means across application versions, as well as across the applications themselves. Finally, from the 550 Sonar rules that were used to generate the issues, we were able to select a limited set that covered more than 50% of the effort for all studied applications. In the case of JEdit, the 9 rules generate more than 75% of the total effort that is required to fix all issues. We observed that a combination of architectural issues, bad coding practices, together with code duplications and unused code, accounted for most of the depth effort. Here, an interesting step further would be to study how these actually translate to observable issues in the software. Finally, we examined the lifetime of discovered issues. All three applications presented issues that remained open across a large number of versions. So we limited our presentation to cover closing 80% of detected problems. Like in the case of research question 2, we studied issue lifetime for both severity as well as type. In the case of FreeMind, both representations are skewed by the large spike in version 0.8.0, which was addressed 2 versions later. Otherwise, we could not identify a correlation between issue lifetime and type, or between issue lifetime and issue severity. In addition, we also carried out a more in-depth analysis, which covered issue tags such as security, performance, and again, we came up empty-handed. So we could not identify a correlation between issue lifetime and any of SonarQube assigned tags. Of course, we know that this can be explained by the fact that, first of all, not all issues translate to observable defects, regardless, perhaps, of issue type or issue severity. We believe that this could be strengthened by the fact that most issues were code smells, and we need a more detailed analysis in order to make sure that this was actually the case. In conclusion, we summarize our main findings from research questions 1, 2, and 3. For each of the applications, we confirmed our past results regarding the unstable nature of early application versions. Mature versions of each application tended to have little variance in the level or in the composition of detected technical depth. Next, the results of conscious refactoring efforts were immediately observable and had a beneficial effect on Sonar's evaluation of code quality. And finally, an important observation is that a small number of common rules generated more than 50% of the total effort across all applications. As such, our next step is to identify the nature of the relation between the issues generated by these rules, their lifetimes, and the effect they have on documented software quality. Thank you for your attention, and for any questions, I'd like to direct you to the email addresses that you find on screen.